Alrighty, so today we're going to be having a look at the general rule for the reciprocal function. So before we get into it, I just want to talk about what is the reciprocal function. This is a reciprocal function. What makes it a reciprocal? Well, it's because x is on the denominator rather than the numerator. We could alternatively write this as x to the negative 1, so we can think of it as a polynomial but with a negative power. Although, remembering our definition from a polynomial, it will not be it's not a polynomial because it's got a negative power. Anyway, but let's have a think about dividing things by something, dividing anything by, or 1 by whatever. And let's think about when this can go wrong. This can go wrong in exactly one particular case, when the denominator, in this case x, is equal to 0. If the denominator is ever equal to 0, that's a problem, because we're not allowed to go 1 divided by 0. That's banned. That's on the not allowed list, like taking the square roots of negative numbers and that sort of thing. It's illegal, not allowed to be done. So before we jump into the general rule, let's just kind of get a sense for this function itself. And what better way to get having a feel of a function than having a look at it in Desmos. So this is the graph of 1 over x, or y equals 1 over x. This is the function. And you can see it's got some interesting behavior. The first interesting bit of behavior is that it has these asymptotes that are sort of running along these lines here. We call these things asymptotes. They're called asymptotes because although this line gets very close, it never will actually touch the axes. And we can actually see that if I get rid of all my markings. If I zoom in, you'll see that it looks like it's pretty much touching, but if I zoom in enough, you can always see that it's never actually touching. And that doesn't just go on the positive x-axis. If I look at the positive y-axis, we're going to get the exact same behavior. It's going to look like it's on the positive y-axis, but of course, it never can actually touch. And so we get this really interesting behavior in which it's kind of only in two quadrants. It's in this quadrant on the top right, and it's in the quadrant in the bottom left. So this is the shape. And the shape, we can sometimes call it a rectangular hyperbola. But for our case, we just need to know this as this is the 1 over x shape. But we said before that x equals 0 was a problem. And now we can see that it is indeed a problem. This function's actually not defined at 0. If we look at the positive part of it over here, it looks as though it's approaching infinity as we go this way. It looks like it's approaching infinity. But when we look at the negative bit, it looks like it's approaching negative infinity. So if something's both approaching negative infinity and infinity, well, what is it really approaching? The answer is it's not approaching anything, and so we can't really understand it in any sort of way. So we say that at x equals 0, this function is undefined. Which makes sense, because if we had 1 over 0, that would be bad. We should not want to have that to happen. So now that we know what the shape is, which is something like this, there's a rough sketch. Let's start to transform it. So the first transformation we could do is shift it up. And to shift it up, well, I could just add a constant on to the end. Let's call it c. And that would basically move the whole thing up vertically. So my new one would look something like this, where the asymptote, this horizontal asymptote, has been moved up to y equals c, whatever the value of c is. It's basically shifted the whole thing up. But because of that, it's also moved the asymptotes, and so it's actually moved it across. Alternatively, we could then also move it left and right using our translations. With that, well, we could basically move the intersection of the two asymptotes wherever we wanted. And we could end up with a picture that looks something like this. We have the horizontal and the vertical asymptotes both having moved, where the horizontal asymptote is now going to be y equals c, just like before, but the vertical asymptote is going to be x equals b, for we've shifted the whole thing across b units, which means that the intersection, this point here, is b comma c, so the intersection of the two asymptotes. So we call this one the vertical asymptote. And remember, these asymptotes are like boundaries. You can never touch the asymptotes, but you get infinitely close to them. But that's all well and good. But there's one more transformation we like to do, which is the stretching, dilation, and such. Now, for this, we can just multiply the part without the c by a. So we can get a over x minus b plus c. Because in the end, 1 was just an arbitrary choice. And for this, it's not going to appear to have any difference than the other ones, but it's going to look a little bit different. However, the interesting part is that when a is positive, we're going to get the shape where it's in the first quadrant and the third quadrant, whereas when a is less than 0, we're going to get the decreasing shape, which looks something like this. And so that kind of gives us a general sense of what the graph's going to look like. So I think it's good to get a visual intuition. So you can see here that as I move b to the left or the right, it just moves the whole thing to the left or the right. And in this case, if I actually put an x equals b, and let's make this some sort of dotted line, you can see that it just shifts this vertical asymptote left and right. Alternatively, if I start moving a, it's going to start moving it up and down, and I can visualize that by putting in y equals a. And once again, I will just make it a nice dotted line for effect. Oh, sorry, not y equals a, y equals c. And you can see that as I move this up and down, that the whole shape moves up and down. So we can move it left and right, and we can move it up and down using these different values. Let me turn off x equals that. Let's see what happens when I play with a. So when I make, let's move it back to the origin, and let's play with a. So as I make a bigger, you can see that it gets further and further away from the axes, and as I make it smaller and smaller, it gets closer and closer to the axes, until at 0 it doesn't really know what to do, and in fact it's not a very interesting function, but we can have a look at that later. But then you can see as I go into the negative numbers that we've moved into these quadrants, and you can see that it still moves around in this way, where the quadrants basically define where we're fixed to. So let's have a play with sketching some. So this is f of x equals 5 on over x, and so the first thing I can notice is that b is equal to 0, and so is c. So based on the initial form, f of x equals a on x minus b plus c, you can see that b and c must both be equal to 0, and that a is positive, a being 5, which means it's going to be the increasing shape, which means it's going to look something like this. In fact, that's going to be a very good sketch, because remember, it hasn't been translated anywhere. B and c are both 0. So for my sketch, so on my axes, I know it's going to be a positive shape, so it's going to look something like this, but then it's also going to have the other component down here. And you can see it still has this increasing behavior where it's low to high, although even though it does sort of finish on the x-axis regardless. It still has that increasing shape going through there. So now we can talk about the domain and the range. So the domain and range is actually quite interesting, because the domain is x in the real numbers, and the range is also, is y in the real numbers. But there's one problem point, and the problem point is right here. We said that x is not allowed to equal 0. So how do we notate that? Well, the easiest way is to use a backslash and then curly brackets 0. And this just means the set minus that number. It's a way of like taking out something. Which also means that the range is similarly limited, because if you have a look at the range, yeah, it gets close to 0, but it never actually hits. And same thing here, it gets close to 0, but it never actually hits. So similarly for the range, it's also going to be minus 0. These are curly brackets on either side. And just for completeness, let's maybe put a point on the graph. So for example, if I subbed in f of 1, well, that would give me 5 on 1, which is equal to 5. So I've got the point 1, comma 5. So 1, 5. So let's say that this is 0.15 on the graph. Alrighty, second sketch. So in this case, we've still got c is equal to 0, but this time b is equal to not negative 3, but actually positive 3, which means it's moved 3 units to the right. In this case, a is actually negative. It's less than 0, because negative 1 is less than 0, which means it's going to be this, not the regular shape, it's going to be the reflected shape. So it has been reflected. It doesn't really matter which axes we think about, which it's been reflected in. It's going to look the same shape regardless. Alrighty, so let's go through and think about sketching it. Alrighty, so the first thing I'm going to do is just set up my axes. And this time I'm going to put in my asymptote. So my asymptote in this case is going to be at x equals 3. Because remember, it's been shifted 3 units to the right. So this is now my new focal point. And the x-axis is still part of it, but obviously it's between the x-axis and this point. Now, because it's been reflected, we're going to get a shape that looks like this. Because remember, it's decreasing. A value is negative. And now I just need to put some labels. Now it's going to have the a y-intercept somewhere here, and it's not going to have any x-intercepts. If you wanted to work out the y-intercept, well, you could just sub in x equals 0 to find that. Previously, in the previous one, there was no y-intercepts. Alrighty, so there's our finished graph, but let's do our domain and range while we're here. So for the domain, we're going to have x is in the real numbers, but this time instead of minus 0, because 0 is actually perfectly fine to sub in, instead the number that's not allowed is going to be 3. Remember, this is x equals 3. So 3 is now the one who's out of luck. So 3 is on the out list, and for the range, it's going to be the same as the previous one. Y is in R minus 0. Alrighty, 1 to go. Alrighty, so this is our last one, and you can see here A is going to be positive, so it's going to be the classic shape. And we can see we both have a B value and a C value. So B in this case is negative 2, and C is negative 3. So it's been shifted 2 to the left, and it's been shifted 3 down. So the first thing to do is to just get ourselves the two asymptotes down. So we've got these are the two asymptotes where this is now the point -2, -3, based on the 2 points. This is the equation y equals -3, and this is the equation x equals -2. So those are the two equations of asymptotes. Since it's the positive shape, it's going to look something like this. There's the picture. You can see that it's actually been moved down a little bit. And in this case, we can kind of see that there should be at least one x and y intercept. So let's see if we can find those. Oh, we'll do domain and range first. So in this case, the domain is going to be x is in the double real numbers, but we've got this problem value, which is at -2 when we think of the x coordinate. And we can think about it if we subbed in -2 here, we'd get -2 plus 2, which is 0, and you cannot divide by 0. So that's why it's not allowed. And for the range, we've got y is in R. And in this case, R is going to be -3. It's a little bit more tricky as to why it's -3, but we can have a think about that. Alrighty, so there's the domain and the range. And lucky last, let's do some algebraic solving. Alrighty, so to find the x-intercept, well, we're just wondering when f of x is equal to 0. So it's 0 is equal to 6 on x plus 2 minus 3. Add 3 to both sides. Alrighty, and this comes our first bit of trouble. We need to multiply both sides by x plus 2, which is exactly what we're going to do. The alternative thing we can think about is think of them both as fractions and then flipping both fractions at the same time. Either way, we're going to basically continue going on. So I'm going to multiply both sides by x plus 2. Let's get rid of this on 1. Now we're going to get 3x plus 2 on the left-hand side, and on the right-hand side we get 6. Now we could expand the brackets, or alternatively, we can just divide both sides by 3, which leaves us with x plus 2 by itself now. Get rid of the brackets. And 2 minus 2, we get x is equal to 0. So, turns out that the x-intercept should be the y-intercept, so we'll just double check that. So the y-intercept is when f of x equals 0, or f of 0, we get f of 0 is equal to 6 on 0 plus 2 minus 3. 6 on 2 minus 3. 6 on 2 is 3, 3 minus 3 is 0. So we get that the x-intercept, y-intercept is the point 0, 0. So I've actually misdrawn this because this shouldn't have actually an x-intercept and a y-intercept, because the x-intercept and the y-intercept are exactly the same, and it's the origin. Alrighty, so here's a little playing with sketching these different functions. I'll see you in the next one. Goodbye.